Welcome back to the deep dive. Today, we are opening up the hood on something that pretty much everyone is using, but I think very few people actually understand the mechanics of.
Yeah, what's really going on behind the curtain?
Exactly. We are talking about the infrastructure of generative AI. And I don't just mean, how do I write a good prompt? I mean, how do we actually build these systems from the ground up?
Exactly. We are moving way past the surface level today. For a long time in the world of machine learning, we were dealing with what we call predictive discriminators.
Predictive discriminators. That sounds very judicial, like a robot judge in a sci-fi movie or something.
It does, doesn't it? But it really just means traditional AI. So systems designed to classify things. Is this email spam or not?
Right. Cat or dog.
Is this a picture of a cat or a dog? Is this credit card transaction fraudulent or legitimate? It's usually binary. It's making a judgment call based on past data.
Okay, so it's basically looking at the world and just putting stickers on things. Cat, spam, fraud.
Precisely. Yeah. But now we've shifted into this whole new era of generative engines. And that shift, it changes everything about how you build the system. We aren't just looking at data anymore. We're creating it.
And I think the core premise we have to start with today, and this was really highlighted in the notebook module on system design we're looking at, is that building the large language model, the LM itself, is actually kind of the easy part.
Relatively speaking, yeah. Easy is a strong word, but in the grand scheme of things,
Yeah.
yes.
The hard part, the really complex part, is building the system around it. The LLMOps.
That's just the crucial distinction. That's everything.
Yeah.
You can go download a model. You can get Llama 3 or Mistral or whatever is current, and you can run it. But that is just a raw engine sitting on a factory floor.
Right.
It's loud, it's dangerous, it consumes a ton of fuel, and if you don't hook it up to a transmission and a steering wheel and brakes, it's not going to get you anywhere useful.
And it might burn down the factory.
And it might burn down the factory. Precisely. So the mission for this deep dive is to unpack all of that infrastructure. We have a few big buckets to fill. We need to figure out how to make these models smart, which is where we get into RAG, or retrieval augmented generation.
Okay.
Then we need to figure out how to make them fast and efficient, which brings us to hardware optimization. And finally, and maybe most importantly, we have to figure out how to stop them from being dangerous.
Which is where we get into all the really thorny stuff like ethics, bias, and security.
Correct. A whole can of worms.
So before we get into the nuts and bolts, let me ask the naive question here. Why isn't a smart model just enough? If I have GPT-4 or Claude or whatever, and it's been trained on, basically the whole internet, why do I need all this extra machinery? Why can't I just ask it questions?
It's a great question, and it's one that a lot of people ask. The answer is, well, it's threefold. First, they hallucinate. They are incredibly confident liars. Second, they get fat and slow. If you want to run them on your own hardware or even just affordably in the cloud, they are incredibly resource intensive. They're huge.
Okay.
And third, and this is a really scary one, they can be tricked. They are vulnerable to injection attacks, they can leak private data, and they can be manipulated into running malicious code.
Okay, so confident liars, fat and slow, and easily tricked. Not exactly the glowing performance review I was expecting for our new AI overlords.
Well, that's why we need the architecture, right? That's why we need to build these architectures of trust.
Let's start with that first problem then. The confident liar problem. I love how the notes title this section, Giving the Model a Brain and a Library. It's such a great distinction.
Yeah, it's the best way to think about it, I think. Standard LLMs, just out of the box, they have a fundamental flaw.
Yeah.
The training data cutoff.
Right, the knowledge freeze.
Yeah.
So if I ask a base model about the winner of the Super Bowl that happened yesterday, and the model was trained back in 2023, what happens?
Well, you get one of two outcomes. It might tell you it doesn't know, which is, the good outcome. That's what you want.
That's the honest answer.
But more often, it will hallucinate. You might confidently tell you that the Kansas City Chiefs won simply because they win a lot, and statistically, that's a very likely sequence of words to follow Super Bowl winner, even if they didn't play.
So it's like a student taking a final exam who hasn't read the textbook since last year. They're just vibing their way through the questions, hoping for the best.
That's a perfect analogy, exactly. They are improvising based on old patterns they've seen. So to fix this, we don't just keep retraining the model every single day. That would cost billions of dollars.
Not feasible.
Not at all.
Yeah.
So instead, we use RAG, retrieval augmented generation.
So break this down for us. This is really about Separating the reasoning from the knowledge. Is that the core idea?
Yes. Think of the LLM not as a database of facts, but as a reasoning engine. It's the brain. It knows how to speak English. It knows how to summarize. It knows how to write code. That's its skill.
It's the processor.
Yeah. It's the processor. The library is all your external data, your company wikis, your internal PDFs, your fresh news articles from this morning. RE is the process of having a librarian go and find the right book from the library and hand it to the brain right before it answers your question.
Okay, I like that. So let's unpack the architecture flow here, because the source material gets pretty specific.
Yeah.
It all starts with something called ingestion.
Right. And this is a really important step. You can't just shove a 300-page PDF into a model and hope for the best.
Yeah.
You have to ingest it properly. You take your documents, PDFs, wikis, Word docs, whatever, and you break them down into chunks.
Chunks.
Small paragraphs, maybe a few sentences, coherent sections of text.
And why do we have to chunk it? Why can't I just feed it the whole book at once?
A couple of really important reasons. One is just cost and efficiency. These models charge by the token, which is roughly a word. Feeding a 500-page user manual into the context for a simple question is incredibly wasteful.
You'd burn through your budget in an hour.
Oh, yeah. But the bigger reason, the more important one, is accuracy. If you give the model too much hay, it really struggles to find the needle. You want to give it just a few bite-sized, highly relevant pieces of context to work with.
Okay, that makes sense. So we chop the document up into these little blocks of text. And then comes the magic part, right? The embeddings. This is a term that gets thrown around constantly.
Yeah.
Vector embeddings. What is actually happening there?
This is, I think, one of the coolest concepts in modern AI. It's really clever. You take that chunk of text, say a paragraph about your company's vacation policy, and you run it through a special kind of model called an encoder model. A common one is from OpenAI. It's called Text Embedding 3.
And what does that encoder do? It doesn't summarize it.
No, it doesn't summarize. It converts it into a list of numbers, a vector.
A coordinate, like a point on a map.
Exactly. A coordinate in a massive multidimensional space. We're talking hundreds, sometimes thousands of dimensions. And the magic is that concepts that are semantically similar, that mean similar things, end up physically close together in that mathematical space.
So in this weird number space, the phrase vacation policy and how to request time off would basically be neighbors.
Exactly. They would be right next to each other,
Right.
even if they don't share the exact same words. Canine and dog would be almost on top of each other. Cat would be close, but a little bit further away. Toaster would be in a completely different galaxy.
Okay, so we've turned our entire library of documents into a galaxy of numbers.
Yes, and that brings us to the next phase, which is storage. We can't just keep these in a spreadsheet. We store these vectors in a specialized database called a vector database. You'll hear names out there like Pinecone, Milvus, or Weaviate.
And what makes them so special?
They are designed to do one thing really, really, really fast. Calculate distance between points in that high-dimensional space.
This is the k-nearest neighbors concept I read about, right?
That's the algorithm they use. So when a user asks a question like, how do I request time off? The system doesn't look for the keywords time and off. That's old school search. Instead, it converts the user's question into its own vector. It finds the coordinates of that question in the galaxy. Then it turns to the vector database and asks, what are the, let's say, the top 3 or top 5 nearest numerical neighbors to this point?
And it grabs those original text chunks associated with those number points.
It retrieves those chunks. That's the retrieval step. And then finally we get to generation. The system takes those 3 or 5 chunks it just found, it pastes them directly into the prompt it's about to send to the LLM, and it adds a critical instruction.
What's the instruction?
It says something like, hey, use only the following 3 paragraphs to answer the user's question. Do not make anything up. If the answer is not in this context, say you don't know.
It grounds the model.
It grounds it completely. It forces the AI to cite its sources, in a way. This reduces hallucinations dramatically because you are not asking the model to remember facts from its training. You're asking it to process and synthesize the facts you just gave it right now.
So it's basically an open book test where you've not only given it the book, you've literally pointed to the exact paragraph where the answer is.
Precisely. And that right there is the backbone of almost every modern enterprise AI application. If you're building a chatbot for your business, you are, at its core, building a RAG pipeline.
Okay, so this is huge. We've given the model a brain and a library. We've built the RAG system to stop it from lying. But here is the next hurdle that comes up in our deep dive outline. How do we know if it's actually working well?
the evaluation problem. This is, and I'm not exaggerating, a nightmare for engineers who are used to traditional software development.
Right, because in traditional software, you write a test. 2 plus 2 must equal 4. If the code outputs 5, it's broken. You fix it. Done.
Exactly. Or even in traditional machine learning, if I build a model to predict if a picture is a cat and it says dog, I know it's wrong. It's a clear failure. But with generative text, it's all subjective. Well, if I ask it to write a summary of a meeting, there are 1,000 ways to write that summary correctly. And 1,000 ways to write it that are just slightly off or a little bit misleading. There's no single right answer to compare against.
Well, how on earth do we grade them? The source material mentions the split between academic benchmarks and reference-free metrics.
Yeah, let's start with the academic benchmarks. These are basically standardized tests for AI, like the SATs for models. The most famous one right now is probably MMLU.
MMLU.
It stands for Massive Multitask Language Understanding.
That sounds intense.
It is. It's a huge multiple-choice test covering everything. STEM, humanities, social sciences. It asks questions about chemistry, about U.S. history, about legal principles. It's testing for broad, general world knowledge. If a model scores high on MMLU, it means it's smart in a general trivia night kind of sense.
Okay, so that's its general knowledge score. And then there's, what was it, GSM 8K?
GSM 8K, yeah. Grade School Math 8K.
Yeah.
That specifically tests multi-step mathematical reasoning. It's not just what is 5 times 5.
It's a word problem.
It's a word problem. Johnny has 5 apples. He gives 2 to Susie. Then he buys 3 more from the store, which sells them in bags of 6. It tests if the model can hold a chain of logic and perform operations in the correct order.
And what about human evil? That sounds different.
That's purely for coding. Specifically, it's for Python function completion. You give the model a function signature and a docstring explaining what it's supposed to do, and you see if it can write the working code to pass a set of unit tests.
Okay, so those are the standardized tests, the SATs for the models. But that still doesn't tell me if my specific RG system, the one I built for my company's vacation policy, is actually working.
Exactly. Your internal HR documents are not in the MMLU dataset. This is where we run into what engineers call the vibes problem.
The vibes problem, you're kidding.
I am not. People will literally say they're checking the vibes. You ask your chatbot a question, you read the answer, you go, the vibe feels right, looks good. But you can't scale vibes. You can't automate vibes for thousands of test cases.
So what's the solution?
We use a really clever technique called LLM as a judge.
Using an LLM to grade another LLM. That sounds dangerously circular.
It sounds circular, but it works surprisingly well. You use a very powerful, expensive, top-of-the-line model like GPT-4 Turbo to act as the judge and grade the output of your smaller, faster, cheaper application.
How does that work in practice?
You give the judge model, GPT-4 everything, you give it the original user question, you give it the context chunks that your AGI system retrieved, and you give it the final answer that your smaller application generated. Then you ask it to score some very specific metrics.
What kind of metrics are we talking about?
The 2 big ones, the ones that really matter for our groundedness and faithfulness.
Yay, let's define those because they sound similar.
They are, but there's a key difference. Groundedness asks, does the retrieved context actually support the generated answer? So if the context says the office is closed on Sundays, and the generated answer is the office is open 24/7, the groundedness score is 0. It's a direct check for hallucination relative to the provided source material.
Okay, and faithfulness.
Faithfulness is a little different. It checks if the answer contradicts the context. It's a subtle distinction, but it's about making sure the model didn't introduce new conflicting information. Essentially, between these 2 metrics, we are programmatically measuring. Did the model stay in its lane and use only the facts it was given?
It's just fascinating that we've had to invent this whole field of, software psychology to figure out if our programs are lying to us.
It is. We've really moved from debugging code to, in a way, debugging reasoning itself.
Now let's pivot. We've got a smart model, we're grading it. But these things are massive. I mean, the large in large language models is not a joke. The source notes mention models ranging from 7 billion to 70 billion parameters.
And that's just the open weights models you can download. The proprietary ones from the big labs are likely in the trillions of parameters.
So section 3 in the outline is fitting the elephant in the fridge. Hardware optimization. Why is this so critical? Why do we need to shrink them?
It comes down to 2 things. Cost and latency. Running a 70 billion parameter model in the cloud is eye-wateringly expensive. Every single token you process costs money. And if you want to run it on-device like on a powerful laptop or inside a specialized server rack in your own data center, you physically might not have enough VRAM.
VRAM, video RAM, the
Like,
memory on the GPUs.
exactly. These models have to be loaded entirely into that super fast memory to work. And a 70B model can take up hundreds of gigabytes. Most computers just don't have that.
So how do we put this elephant on a diet? The first and most common technique seems to be quantization.
Yes, quantization is king right now.
It's a word that sounds very Star Trek, but what does it actually mean in practice?
It's actually based on very simple math. So standard models are trained using 32-bit floating point numbers. We call that FP32.
Yeah.
That means every single weight, every connection in that giant neural network is a number that takes up 4 bytes of memory.
Okay, 4 bytes per number.
Quantization is simply the process of reducing that precision. We say, hey, do we really need 32 bits of precision for every single one of these billions of numbers? Or can we get away with 8 bits? That's int8, an 8-bit integer.
So we're basically rounding the numbers off, making them less precise.
We're lowering the resolution. Think of it like a digital photo. An FP32 model is like a 4K Ultra HD RAW photograph. It's got perfect, crisp detail. An intake quantized model is like a high-quality JPEG.
Ah.
It looks almost exactly the same to the human eye. You can't really tell the difference, but the file size is way, way smaller.
And the notes say intake quantization reduces memory usage by about 73%. That's not a small number.
It's a game changer. You go from 4 bytes per weight down to 1 byte per weight. That's a 75% reduction, roughly. It is literally the difference between needing 4 top-tier, very expensive GPUs and just needing 1.
And what's the trade-off? Does the model get dumber? Does the accuracy just fall off a cliff?
That's the amazing part. For these very large models, the accuracy loss is almost always negligible. It turns out these neural networks are incredibly robust. They have so much redundancy that you can lose a lot of precision in the individual weights without really changing the overall output behavior of the model.
The notes mention a specific formula here, a fine quantization. Is that important?
It's just the math behind how we map the big numbers to the small numbers. It involves a scale factor, which we call S, and a 0 point, which we call Z. It's basically just a linear equation. You take the original range of values, say from negative 15.7 to plus 20.3, and you just squash them proportionally into the range of negative 128 to 127, which is what an 8-bit integer can hold.
Okay, so that's quantization, making the numbers smaller. The other big technique mentioned is pruning.
Pruning is exactly what it sounds like. You are trimming the hedge, you're a gardener. You look at this massive neural network and you say, hey, this connection here, this weight, its value is basically 0. It's not contributing anything meaningful to the decision-making. Let's just cut it.
You literally set it to 0.
You set its value to 0. Now, there are 2 ways to do this, and the difference is really important. There's unstructured pruning and structured pruning.
Unstructured sounds messy.
It is messy. Unstructured means you just go through and you zero out individual weights wherever you find them, one by one. The problem is you end up with what's called a sparse matrix.
Okay.
Imagine a giant spreadsheet where half the cells are empty, but they're scattered completely randomly all over the place. Computers and GPUs actually hate that. It's really hard to do math efficiently on a Swiss cheese matrix unless you have very specialized hardware designed for it.
So you don't actually get a speed up from doing that?
Often, no. You save memory space, but the model doesn't actually run any faster, which is often what you really care about.
Yeah.
That's why structured pruning is gaining a lot of popularity.
And how is that different?
Instead of removing individual weights like crumbs, you remove entire structures. You delete a whole neuron. You delete a whole channel or a filter. You might even delete an entire layer of the network.
So you're taking a whole slice out of the cake instead of just picking out individual sprinkles.
Exactly. And the benefit is that this physically shrinks the matrix. The computer sees a smaller but still dense rectangular matrix, which it loves. It knows how to do math on that very fast. You get speed-ups on standard off-the-shelf hardware.
Okay, so we've got ORAG to make it smart, quantization and pruning to make it fast and fit in the fridge. Now we have to talk about the dark side of this. Section 4, the mirror problem, ethics and bias.
This is where the engineering really meets sociology, and it's absolutely critical.
The key point here in the notes is that bias isn't just bad data, it's a systemic behavior.
Right. And people often have this misconception. They think, oh, the model is biased, just go find the bad data and clean it. But it's so much more complex than that. To really understand it, we need to categorize the type of bias we're dealing with. The notes list 3 very specific and very different types.
Let's go through them. The first one is historical bias.
Historical bias is, I think, the trickiest one because it happens when the data reflects the world perfectly. But the world itself was and is biased.
The example given is a model for hiring CEOs.
Right. Imagine you train a model on hiring data from, say, the 1970s and 80s, and you ask it to predict who will make a good CEO. The model will look at that data and say, oh, I see a very clear pattern. Almost all the successful CEOs in this data set are men. Therefore, being a man is a strong predictor of success as a CEO.
The model isn't wrong about the data it was given. The data is an accurate reflection of history.
Exactly. The model is being statistically correct, but it's being ethically and morally wrong. It's perpetuating a historical inequality. And you can't just clean this data because the bias is baked into reality itself. You have to actively intervene in the model's reasoning process or the system's output to correct for it.
Wow. Okay, then there is a second type, representation bias.
This one is a bit more straightforward. This is when your data collection process was just flawed. The classic example is the ImageNet dataset. For a long time, the massive data sets used to train image recognition models were heavily skewed toward Western countries, mostly images from the US and Europe.
So it recognized a bride in a white wedding dress perfectly.
Flawlessly. But it would completely fail to recognize a bride in a traditional Indian wedding sari because it simply hadn't seen enough examples. The sample wasn't representative of the world. Now that can be fixed by going out and getting better, more diverse data.
Okay. And the third one is measurement bias. This one feels a little more subtle.
It's very subtle and very dangerous. This happens when we use a proxy for something we actually care about, but the proxy itself is flawed. The example in the notes is perfect, using arrest rate as a proxy for crime rate.
At first glance, they sound like the same thing.
They absolutely are not. Arrest rate is a function of policing. If certain neighborhoods are policed more heavily than others, the arrest rate in those neighborhoods will go up, even if the underlying crime rate is exactly the same as in a less policed neighborhood.
Ah.
So if you train a model to predict high crime areas, but you feed it high arrest areas,
Yeah.
you are not building a crime prediction model. You are building a model that reproduces the existing biases of the policing strategy.
That is a crucial distinction. It really shows that you can't just be a coder to build these things. You have to be a critical thinker. You have to be a sociologist almost.
You have to understand the provenance and the context of your data, absolutely.
Speaking of data, let's move on to privacy. Section 5, keeping secrets. Because these models are hungry. They eat everything you feed them.
And they have a very bad habit of regurgitating it at the worst possible moments. We call this the PII, risk personally identifiable information. If a model is trained on a bunch of sensitive internal company emails, it might accidentally autocomplete a sentence with someone's real social security number or their home address.
That's a huge liability. So how do we stop that? The notes dive into a concept called differential privacy.
Differential privacy, or DP, is really the gold standard here. It's a formal mathematical definition of privacy. It's not just a guideline, it's a guarantee.
So how does it actually work?
Okay, imagine you have a database of people's salaries at a company. If I, as an analyst, query the database and ask for the average salary, I get a number. Then, if I remove one person, let's say I remove Bob from the database, and I ask for the average salary again and the number changes significantly, I might be able to work backwards and figure out Bob's exact salary.
Right, especially if he's the CEO or something.
Exactly. Differential privacy provides a mathematical guarantee that the output of the algorithm is essentially the same, whether or not any single individual's data is included in the dataset.
So Bob becomes invisible in the aggregate data.
He's statistically invisible, yes. And the way we achieve this in AI model training is by adding carefully calibrated noise. We add random static, usually from a Laplacian or Gaussian distribution, to the gradients during the training process. This technique is called DPSGD.
But wait, doesn't adding a bunch of noise and static mess up the learning process?
It does, and that's the fundamental trade-off. We have a concept called the privacy budget, which is denoted by the Greek letter epsilon. If you want perfect privacy, a very low epsilon, you have to add a ton of noise. But then your model might not learn anything useful. The data is too blurry.
And if you want a perfect model?
If you want a perfectly accurate model, you add zero noise, which gives you zero privacy. The whole game is finding the sweet spot in the middle that your application can tolerate.
The other mechanism mentioned is k-anonymity. That sounds a bit simpler.
It is much simpler and easier to implement. It's about hiding in a crowd. K-anonymity is a property of a data set, that ensures any given record is indistinguishable from at least k-1 other records in that data set.
So if K is 5, I can narrow it down to a group of 5 people, but I can't tell which of those 5 is the person I'm looking for.
Exactly. And you achieve this through two main techniques: suppression, which is just deleting sensitive columns entirely, like the name column, or generalization. Instead of listing an exact age like 24, you change it to a range like 2030. Instead of a specific zip code like 1001, you generalize it to 100XX. You just blur the details until the individual disappears into the group.
Okay, we're almost to the end of the stack. This is a lot. We've covered RAG, optimization, ethics, privacy. Now the final line of defense: security, locking the doors.
This is where we stop treating the model like some abstract brain and start treating it like what it is: a software artifact. It's a file on a computer, and files can be very dangerous.
The expert warning in the notes here is honestly chilling. It says, models are essentially executable code.
They are. And this is not an exaggeration, especially in the Python ecosystem where most of this work is done.
So let's talk about the specific danger they mention: the pickle risk.
Oh, the pickle risk. This is a classic, well-known problem in the Python world. PyTorch, which is the most popular library for building and training these AI models, typically saves its models as .py files. Under the hood, these files use a serialization format called pickle.
And what's so wrong with pickle?
Pickle was designed to be extremely powerful and flexible. It allows you to save and load arbitrary Python objects. But that power is its downfall. It means when you load a pickle file, the computer isn't just reading data, it is executing the instructions inside that file to reconstruct the object.
So if I download a cool new model from some random forum on the internet?
You are doing the digital equivalent of finding a random.exe file on a sketchy website and just double-clicking it. A hacker can hide a malicious script inside the model weights that says delete all files on this computer, or find all the AWS secret keys and send them to this IP address. And the moment your code runs torch.load, that script executes.
That is genuinely terrifying. Is there a fix for this?
Yes, thank goodness. The industry is rapidly moving to a format called safe tensors. It's a secure alternative that was designed specifically to fix this problem. It only stores the tensor data, the numbers, and absolutely no executable code. If you are downloading models from places like Hugging Face, always look for the safe tensors files.
That is a very good tip. Now, what about the container itself? The Docker image that's running the model in production?
That brings us into standard but crucial supply chain security. You need to be scanning your containers. There are great open source tools like Trivy or Claire that will scan your Docker image and check for CDEs, common vulnerabilities, and exposures.
And what's it looking for?
It's looking for known security holes in all the libraries you're using. Maybe the version of Python you have in your container has a known bug. Maybe the OpenSSL library is outdated and vulnerable. You need to find and patch those holes before you deploy to production.
And then there's signing.
This is all about the chain of custody. You use tools like cosign or sigstore to cryptographically sign the model file and the container image itself. It's like putting a digital wax seal on an envelope.
So you can be sure it hasn't been tampered with since it was built.
Exactly. When your Kubernetes cluster in production tries to start the pod, the first thing it does is check the signature. If the seal is broken, if someone, an attacker, has swapped out your safe model for their malicious one, the cluster will simply refuse to run it.
And finally, good old-fashioned access control, RBAC.
The principle of least privilege. This is Security 101, but people get so excited about AI that they forget it. Does your data scientist who's just training models really need write access to the production inference cluster? No, absolutely not. They need read access to the training data in an S3 bucket.
And what about the robot itself, the model in production?
The service account that the model's pod is running as. It should not have admin access to your entire cloud database. It should only have access to the specific tails and features it absolutely needs to do its job. Because if that model gets compromised by something like a prompt injection attack, you don't want the attacker to suddenly have the keys to the entire kingdom.
Okay, wow, let's try to wrap this up. We have covered a massive amount of ground here.
We really have. It's a big landscape.
We started with a raw, powerful, but kind of dumb and hallucinating model. We gave it a library to read from with R. We invented a way to grade its essays with LLM as a judge. We put it on a diet with quantization. We checked it for historical bias. We gave its data a privacy cloak with differential privacy. And then we locked it in a signed, secure container with safe tensors.
That is the architecture of trust. Each one of those pieces is a critical layer.
It really, really drives home the point we started with. The AI part, the neural network, is just the engine block. The actual car, the thing you can drive safely on the road, is built out of all these other incredibly complex and important parts.
And without those parts, that engine is just a very noisy, very expensive, and very dangerous paperweight.
So, to leave our listeners with something to chew on, here is the final provocative thought for today. We talked about optimization and making things fast and small. And we talked about safety things like privacy budgets and groundedness scores.
Constant tension between the two.
Yeah,
Performance versus safety.
exactly. So here's the question. If a model is optimized to be 99% accurate on a benchmark, and it's lightning fast because you use innate quantization, but it regularly fails the groundedness score, meaning it's making stuff up,
Right.
or it leaks PII because you set the privacy budget too high to keep its utility up, is that model actually intelligent?
Or is it just a very sophisticated but very dangerous parrot?
That is the question. Where do you, the listener, draw the line between optimization and safety in your own use of AI? Are you building a system that's safe to drive, or are you just building one that goes really, really fast right up until the moment it crashes?
That's the challenge for every single AI engineer and product manager out there today.
Thanks for diving deep with us. We'll see you in the next one.
Stay curious.